Swayam Prabha. Digital India. Educated India.
Hello all, welcome back. In the couple of previous lectures, we were discussing about subsurface water and infiltration process. Now we know what is meant by actual infiltration, potential infiltration. Also we have seen the well known equation that is termed as Richard's equation, which describes the flow through the unsaturated porous medium. Today we are going to see another equation which can be utilized for finding out infiltration rate and cumulative infiltration, that is Green-Ampt equation. Green-Ampt equation is derived in the year of 1911. So, this provides an exact analytical solution with certain approximation to the flow. Some of the approximations are made related to flow through unsaturated zone, and then this equation has been derived. This is derived based on the fundamental principles, that is based on the continuity and momentum equations. First we will derive the continuity equation and then momentum equation. After that, combining these two fundamental equation, Green-Ampt equation is derived. So, in this, wetting front is assumed as a sharp boundary dividing the saturated and unsaturated zone. While we were discussing about the soil moisture profile, we have seen different zones beneath the ground surface. It has been divided into 4 zones. So, in this case we are not considering different zones, we are considering 2 zones only, that is the unsaturated zone and the saturated zone. Saturated zone is above the wetting front and unsaturated zone is with the initial moisture content which is coming below the wetting front. So, other zones which are transmission zone, transition zone, these zones are not taken into account. So, this equation, before starting the derivation, we need to have the idea about different parameters considered. So, first let us have a look into the soil moisture profile. This is the ground level, and along the vertical axis, that is the z axis, we are marking the depth beneath the ground surface. Then along the x direction we are marking the moisture content. So, as similar to the soil moisture profile which we have discussed in one of the lectures, we are considering the soil moisture profile here also, but only difference is that we are not considering all the 4 zones, we are having the saturated zone and the unsaturated zone in this case. So, moisture content is marked along the x axis, and here in the derivation of Green-Ampt equation, we are considering the depth of water on the ground, that is ponded depth due to rainfall as H naught. So, this equation is for ponded condition. That means, this equation is giving you the potential infiltration. What is potential infiltration? If sufficient quantity of water is available for infiltration, that is the potential infiltration. That is maximum infiltration which can happen within a soil at a given point of time. So, when ponding depth is there, means sufficient amount of water is available for infiltration. So, here we are considering H naught above the ground surface as the ponding depth. Now, what we are assuming, the wetting front is continuously moving down. So, this is a sharp wetting front and it is moving continuously in the downward direction as the rainfall is infiltrating into the ground. So, which is considered to have a depth of L. That is, given time t, we are considering a wetting front which is at a depth of L. Now, in the beginning of infiltration, the length is 0 and as the water infiltrates into the ground, at time t, we can consider the length of wetting front or the depth of wetting front to be capital L. Now, theta I is the moisture content below the wetting front. So, that is the initial condition. At the beginning or at time t equal to 0, when there was no infiltration, entire soil was having the moisture content of theta I, which was at initial condition. Once the rainfall started and the infiltration process started, water is infiltrating into the ground and the moisture content changes to the moisture content at that particular time t. So, at time t, we are considering wetting front has reached a depth of L and above that we are having the wetted soil and below that we are having the dry soil which is at the initial condition. And porosity of the soil. Porosity is the maximum moisture content. Soil can hold maximum quantity of water up to porosity of the soil. That is represented by eta. So, this much is the maximum moisture content, this much can be the maximum moisture content represented by the porosity. Now, another term you should be familiar is that theta r, that is the residual moisture content. Residual moisture content is the moisture content which is present in the soil. If you are drying the soil and beyond which we cannot dry during the ambient condition, some amount of moisture will be present in the soil as residual moisture content if you are drying the soil at ambient conditions. And this is the, that is theta r is already there in the soil. Beyond that, how much pore space is available for moisture to be stored, that is represented by effective moisture content theta e. And above the wetting front, we are having the wetted zone which is having hydraulic conductivity K. So, we are considering hydraulic conductivity of wetted zone to be capital K and below that we are having the dry soil. We can see different parameters. H naught is the ponding depth at soil surface, then K hydraulic conductivity, eta is the porosity, theta E is the effective porosity. That can be represented by eta minus theta r. That is, initially we are having a moisture content, that is the residual moisture content. Beyond that, how much is available, that is eta minus theta r. That is represented by effective porosity. Theta is the moisture content at any time, that is between theta I and eta. So, initial moisture content is theta I, but in the soil which we are considering, it is having certain moisture content present which is represented by theta I. So, theta is the moisture content which can be between initial moisture content theta I and the porosity, that is the maximum moisture content, porosity eta. So, theta is marked between theta I and eta. Theta r is the residual moisture content in the soil beyond which it cannot be dried out under ambient conditions. Now, we are going to derive the fundamental equations, that is our mass conservation equation and the momentum conservation equation based on control volume approach. So, for that we need to consider the control volume. So, take a control volume below the ground surface within the depth of infiltration water. Water is getting infiltrated into the ground. How the soil moisture profile is approximated for the derivation of Green-Ampt equation we have seen already. So, within that depth of infiltrated water we are considering the control volume. Green-Ampt equation will be derived as a combination of continuity equation and momentum equation. First, we are going to derive the continuity equation. So, for that we need to have the idea about the control volume. So, what we are going to do? We are going to consider a vertical column of soil of unit horizontal cross sectional area as the control volume. Beneath the ground surface, a soil column, cylindrical column which is having a cross sectional area A which is equal to unity is considered for deriving the continuity and momentum equations. So, this is our ground level. Control volume is equivalent to the cylindrical length of L. So, this control volume is a cylindrical column of soil which is having a unit cross sectional area. How much is the depth of the control volume? It is equivalent to length L which is considered between two sections 1 and 2. This much depth is considered as the control volume depth, and this equation is derived based on the assumption that potential infiltration is taking place. Sufficient quantity of water is available for infiltration process. So, there is a ponding depth we are considering. Water is getting ponded above the ground surface which is having a depth of h naught. Now, initial moisture content we have seen, that is represented by theta I. This is the ponded depth. Now, water is infiltrating into the ground, and as it infiltrates the soil becomes wet, and we have considered a time the wetting front has reached at the section 2. So, above this wetting front we are having the wet soil, and below that we are having the dry soil which is having the initial moisture content of theta I. So, this will be infiltrating into the ground again and again deeper as time proceeds. So, wet soil is marked with different color, and beneath that we are having the dry soil. Wet soil and dry soil is separated by the wetting front. So, this is one assumption. Sharp wetting front we are considering, that wetting front is separating dry soil and wet soil. So, above the wetting front we are considering completely saturated zone, and beneath that it is unsaturated. Now, we are going to derive the continuity equation, that is the mass conservation equation. So, amount of water stored in CV due to infiltration at any time we need to quantify. So, volume of the CV, first we need to get the volume of CV, cross sectional area is unity and depth is L. So, volume of CV is L into area, that can be written as L multiplied by 1, that is equal to L. Now, we need to get the water stored in control volume due to infiltration at any time t. What is the total amount of water stored? So, it can be represented by cumulative infiltration, that is the amount of water infiltrated within a time t. We are having the expression for volumetric water content, that is given by volume of water divided by total volume of soil sample. Here we are having the total volume of soil sample as A multiplied by L, that is equal to L. So, we are having the volume of CV. So, we can get volume of water by making use of theta multiplied by total volume of soil sample. That is nothing but our cumulative infiltration F of t. F of t is given by L multiplied by eta minus theta I. Why eta minus theta I? So, you look at this expression, that is for volumetric moisture content, that is volume of water divided by total volume of soil sample. We have assumed that at time t the wetting front has reached a depth of L. Above the wetting front we are having the saturated zone. Saturated zone means our moisture content has reached the porosity value, maximum value. But initially itself the soil was having some initial moisture content theta I. So, how much extra is added? Moisture content change has taken place from theta I to eta. So, within this interval of time the quantity of water which is infiltrated represents a moisture content of eta minus theta I. So, eta minus theta I multiplied by the volume of soil sample will be giving you the water stored in the control volume within time t. So, that is what is represented by equation F of t, that is equal to L multiplied by eta minus theta I. That can be written as L delta theta. Delta theta is nothing but eta minus theta I, that is the amount of moisture content in excess of initial moisture content. So, this is our continuity equation. So, this is very simple. What we have considered, we have considered a control volume which is having a cylindrical area and the depth L, and how much is the volume of the control volume we have calculated. If total volume of the control volume is known to us, that total volume multiplied by the moisture content will be giving you the total quantity of water stored. So, the moisture content maximum, that is, it is in the saturated region, maximum it can go up to eta minus theta I, because we were having some initial moisture content theta I. So, that way we have quantified the cumulative infiltration given by f of t is equal to L delta theta. Delta theta is only a representation for eta minus theta I. This is the continuity equation. Now, let us move on to the derivation of momentum equation. Momentum equation is very much familiar to us, which is given by the Darcy's law. That is nothing but Q is equal to minus K del H by del Z. So, here we do not have to derive the momentum equation. We already have the equation Q is equal to minus K del H by del Z. Only thing required is corresponding to del H and del Z, we need to substitute here values based on the control volume which we have considered. Q is the flux, the Darcy's flux. Here in this case, the infiltration rate. So, Q is negative downwards. Upwards z direction is considered as positive and downwards z direction is negative. So, infiltration is the process which is taking place in the downward direction. So, definitely it will be having negative sign. We need to consider that negative sign. So, F is nothing but minus Q. Rate of infiltration F is equal to minus Q. Now, we need to get expression for del H by del Z. Del H by del Z can be written as H1 minus H2 divided by Z1 minus Z2. We have considered two sections, section 1 at the ground level and section 2 where the wetting front depth is considered. So, between this we need to calculate, considering section 1 and section 2, what is del H by del Z. It can be written as H1 minus H2 divided by Z1 minus Z2. Now, we need to find out the representations for H1, H2, Z1, Z2. So, here this Darcy's equation we are rewriting, F is equal to, Q is substituted as minus F. So, minus is there on both the sides. So, minus gets cancelled, F will take the form K multiplied by H1 minus H2 divided by Z1 minus Z2. This is the equation for infiltration rate. Small f is representing the infiltration rate. So, we got the infiltration rate equation from the Darcy's law. So, now for writing the expressions or the notations related to H, Z, all those things, we are again considering the control volume. So, at section 1 is at ground level and section 2 at the wetting front. On the ground surface, we are having H1, that is at section 1 the head is H1. What is that? It is the ponding depth, that is head causing the flow is the ponded depth of water. So, H1 is equal to H naught and Z1 will be, datum head will be equal to 0, because we are considering the datum as the ground surface. So, this thing should be carefully understood. The datum is considered at the ground level, and if the datum is ground level at that location, that is our section 1, so datum head Z1 will be equal to 0, and corresponding to the head H1, head which is causing the flow of fluid, that is in the positive upward direction. So, it can be written as positive H naught. So, that we can tabulate. At section 1, we are having pressure head to be H naught and datum head is Z is equal to 0 and total head will be H naught. Now, coming to section 2. Section 2 is at the location of wetting front. So, what we are going to do, wetting front properties are considered to be unsaturated. That is the sharp boundary which is separating the unsaturated and saturated region. So, at the wetting front, the properties which we are considering is that of the unsaturated region. Wetting front is considered as unsaturated. So, only negative pressure will be there. In the unsaturated zone, the head causing the flow, main component is the suction head. We have seen that is the negative pressure head. So, that negative pressure head is the suction head, and suction head and the datum head, these two are the two components of head causing the flow within the unsaturated region. So, now we need to write expressions for this suction head and the datum head at section 2. So, at section 2, energy causing the water movement is due to suction head and datum head, that can be represented by pressure head, that is our suction head can be represented by minus psi, and datum head. Look at this figure. At section 2 we are considering, here we know the depth of the wetting front is L, but that is below the ground surface, below the datum, that is moving in the downward z direction. So, it has to be considered with a negative sign. That is what is tabulated here. Datum head is negative L, Z2 is equal to minus L, and pressure head is psi, that is representing the negative pressure, that is why we have put the sign minus psi. So, we are in the, while deriving the expression itself, we are considering the sign over here, negative sign is considered. So, total head will be minus psi minus L. So, we got the expressions corresponding to H1, H2, Z1, Z2. Head causing the flow at section 1, head causing the flow at section 2, and corresponding to two sections 1 and 2, what is the datum. Now, we are going to Darcy's law and substitute these values. Q is equal to minus K del H by del Z. We have seen it can be written as F is equal to K H1 minus H2 Z1 minus Z2. Here in this case, we will substitute for H1 H2 Z1 Z2. Z1 and Z2 are Z1 equal to 0 at the ground surface and Z2 equal to minus L, because it is beneath the ground surface or beneath the datum or in the downward Z direction. So, once we substitute in this particular equation will be F is equal to K H naught is our ponding depth, H naught minus, that is H1 is represented by H naught, that we have tabulated already in the previous slide. H naught minus, what is H2? H2 is given by this value, that is minus psi minus L, divided by Z1 minus Z2, that is H naught minus psi minus L divided by Z1 0, Z2 is minus L, 0 minus minus L. It will be taking the form of K multiplied by H naught plus psi plus L divided by L. So, F is given by K H naught plus psi plus L divided by L. Now, what we are going to do? We are going to assume in this equation we are having H naught ponded depth and psi L divided by L. So, H naught, that is the ponded head, if we are comparing with the suction head and the datum head, it is very small. That is why what we are going to do? We are going to neglect the value of H naught. While comparing with other head, we can neglect the value corresponding to ponding depth. So, the expression for infiltration rate or the momentum equation takes the form F is equal to K multiplied by psi plus L divided by L. This is the equation corresponding to our infiltration rate, that is potential infiltration. Now, we can write F is equal to K mod of psi plus L divided by L, because this psi is already incorporated the negative sign. So, if some numerical problem you are solving, suction head is given as some centimeters. So, even though it is negative pressure head, you do not have to consider the sign there, because while deriving the Green-Ampt equation itself, we have considered that sign, and final expression was not having any sign over here in this case. So, we can put, in order to avoid confusion further, we are putting the mod sign to substitute the value without sign, since we have already incorporated the sign of psi while deriving the equation. This is our momentum equation. So, now the fundamental equation such as conservation of mass and conservation of momentum equations have been derived by making use of the control volume approach for the process infiltration. So, now continuity equation is F is equal to L delta theta, and momentum equation is given by in small f is equal to K psi plus L divided by L. Capital F is representing the cumulative infiltration and small f is representing the infiltration rate. So, here we are with the expressions corresponding to cumulative infiltration and the infiltration rate. But we are having knowledge that small f, that is the infiltration rate, is nothing but the differential of the cumulative infiltration with respect to time. Small f is equal to df divided by dt. So, df by dt is given by K psi plus L divided by L. So, this equation we need to look into again. These are the two equations. Df by dt is equal to K psi plus L divided by L, and our continuity equation is giving the cumulative infiltration, that is capital F is equal to L delta theta. So, L, that is the depth of the wetting front, that is present over here also, but at a time t, how much is the depth of wetting front, we do not have any idea. So, what we will do, we will make use of the continuity equation, and L is represented by cumulative infiltration divided by delta theta. So, combining both the equations, we will get, for L in this equation, we will substitute this expression from the continuity equation. So, the equation takes the form like this: df by dt is equal to K multiplied by psi plus f by delta theta divided by f by delta theta. So, denominator we are having delta theta. So, that is equal to, it will be giving us df by dt is equal to, some rearrangements we are doing, df by dt is equal to K psi delta theta plus f divided by f. So, the expression changed to this form, and what we are doing, this equation is df by dt. It is a differential equation. So, our intention is to get the expression for infiltration rate small f and the cumulative infiltration capital F, right. So, df by dt is given by this equation. So, that we will rearrange the terms of similar kind, and after that, for getting the infiltration, we will be integrating that particular equation. So, these terms have been rearranged in such a way that it will look like this: f divided by f plus psi delta theta df is equal to k dt. Now, using the method of variable separation, we will rearrange this particular term for making the expression to be in the simple form. So, f divided by psi delta theta plus f is written as, numerator we are making some changes, that is psi delta theta plus f minus psi delta theta. So, this can be written as, substituted over here, psi delta theta plus f divided by psi delta theta plus f minus psi delta theta divided by psi delta theta plus f df is equal to k dt. So, this particular term will be equal to 1. So, next we are proceeding for that, it will be taking the form 1 minus psi delta theta divided by psi delta theta plus f df is equal to k dt. So, we are going to integrate the both sides of the equation. So, left hand side is something related to cumulative infiltration, right hand side is something related to time. So, integrating limits will be, for the left hand side it will be at the beginning 0 infiltration, cumulative infiltration is equal to 0. So, it will be varying between 0 to cumulative infiltration at time t. So, that is why we are putting the limits as 0 to capital F of t, that is the cumulative infiltration at time t, 1 minus psi delta theta divided by psi delta theta plus f df, and right hand side the time is varying between 0 and t. 1 minus psi delta theta divided by psi delta theta plus f, we are again making some rearrangements. So, this can be modified as 1 minus, we are dividing by numerator and denominator of the second term by psi delta theta. So, it will be taking the form 1 minus 1 divided by 1 plus f divided by psi delta theta. Now, this will be substituted here in this equation. So, the equation takes the form like this. So, we are separating the left hand side into two terms. So, it will be taking these two, taking in this form, and now we are having three terms, one term on the right hand side and two terms on the left hand side. So, integral of 0 to f of t df minus 0 to f of t, this particular expression is equal to 0 to t k of dt. So, these two terms, this term and this term, it is very simple. So, that we can integrate first 0 to f of t. So, it will be taking the values f of t minus 0 minus second term is equal to k multiplied by t minus 0. So, it will be f of t minus 0 to f of t 1 by 1 plus f divided by psi delta theta df is equal to kt. Let this equation be 1. So, this is our expression. We are going to consider the second term separately. For integrating this, we are going back to our basic calculus and making use of one particular integral. 0 to x a divided by a plus x dx can be taken. So, what is the solution for this integral? That is a ln x plus a. You can compare these two expressions within the integral. Integrand we are comparing. So, instead of a we are having 1 and a plus x, 1 plus x is given by this complete quantity. So, we will be making use of this particular relationship for finding out the solution of this integral. So, that can be written as integral 0 to f of t 1 by 1 plus 1 divided by psi delta theta f df. So, this will be taking the form ln x plus a in our case is 1. So, ln 1 plus f divided by psi delta theta, and one coefficient is there, that is 1 by psi delta theta. So, while integrating it will be coming as 1 divided by 1 by psi delta theta. This can be rearranged to get the final expression, that is psi delta theta ln 1 plus f divided by psi delta theta. So, this is the solution for this integral. Now, we can substitute in the equation 1 f of t minus 0 to f of t 1 by 1 plus f divided by psi delta theta df is equal to kt. So, here we will substitute this particular solution of this integral. After substituting, it will be taking the form f of t minus psi delta theta ln 1 plus f of t divided by psi delta theta is equal to k of t. F of t can be written as k of t plus psi delta theta ln 1 plus f of t divided by psi delta theta. This is the Green-Ampt equation for cumulative infiltration. Green-Ampt equation for cumulative infiltration is given by this equation, and Green-Ampt equation for infiltration rate is given by this particular equation. That is, one as cumulative infiltration is in terms of f of t and infiltration rate is in terms of small f of t. We have made use of the continuity and momentum equations, and momentum equation directly gave the equation corresponding to infiltration rate, and by making use of the momentum equation and continuity equation, we got the equation corresponding to cumulative infiltration. These are the two equations corresponding to infiltration rate and cumulative infiltration. Now, small f of t is given by this equation. F of t is there on the infiltration rate is there on the left hand side, capital F of t there on the right hand side. So, infiltration is present on both the sides. If you look at the cumulative infiltration also, capital F of t is present on both the sides. So, finding the solution of this equation is not that easy. So, it is non-linear implicit equation. For that, we may have to go for some of the iterative methods to solve these equations. So, some methods are trial and error method, Newton-Raphson method and successive approximation method. Any of the methods for solving these type of implicit equation from mathematics can be utilized for getting the solution of these equations. Now coming to Green-Ampt parameters, these are the two equations, cumulative infiltration and infiltration rate. So when you look at these equations, we can tabulate the Green-Ampt parameters. We are having the hydraulic conductivity present K, then we are having the suction head psi. Here we are having delta theta is given by eta minus theta I. So eta is the porosity, theta I is the initial moisture content. So theta I or SC, effective saturation, these two terms can be utilized for representing the initial condition. So different Green-Ampt parameters we can summarize by looking into this equation, that is the hydraulic conductivity K, suction head psi, eta porosity and theta I, that is the initial moisture content. Now we need to understand what is SC. SC is the effective saturation. If we are that particular quantity we are assuming to be constant for a given time, given instant of time. How it is defined? It is defined as the ratio of the available moisture divided by the maximum possible available moisture in the soil. So this definition is given by Brooks and Corey in the year 1964. Even though Green-Ampt equation is derived in the year of 1911, this making use of effective saturation concept has come from Brooks and Corey's theory. What is effective saturation? Effective saturation is the ratio of available moisture content to the maximum possible available moisture content. Available moisture content is the moisture content at that particular instant of time, maximum how much the soil can withhold. So that can be written by making use of the formula SC is equal to theta minus theta R divided by eta minus theta R, available moisture content, that is the at a particular time instant moisture content is theta, and initially itself we were having a moisture content of residual moisture content. So at the particular time instant the available moisture content will be theta minus theta R, and what will be the maximum possible this available moisture content? It will be porosity minus theta R. That is what is represented over here in the equation. SC is given by theta minus theta R divided by eta minus theta R. So theta can vary between theta R to saturation, eta. So you look at this equation, theta will be varying for different times. So when theta can vary between theta R and eta. So if you are substituting theta R for theta, what will be SC? Theta R minus theta R, it will be 0. And if you are substituting eta for theta, eta minus theta R divided by eta minus theta R. So SC can vary between 0 and 1. When theta is equal to eta, SC will be equal to, saturation will be 100%. All the pores are completely filled with water. Effective saturation can vary between 0 to 1. So now we need to have an idea about effective porosity theta E. Theta E is marked in the initial soil moisture profile. There you have seen what is theta E. So we are having the expression for effective saturation theta minus theta R divided by eta minus theta R. So theta E is given by eta minus theta R. Maximum is eta minus residual moisture content, that is the effective porosity. So theta E is equal to eta minus theta R. So from this we are going to get the expression for theta minus theta R. Theta minus theta R is given by SC multiplied by eta minus theta R. So theta minus theta R can be written as SC multiplied by theta E. Theta E is our effective porosity. Now we are going to make use of the initial condition when theta is equal to theta I, initial that is volumetric moisture content theta I. So here we are going to substitute for theta by means of theta I. So SC can be written as at the initial state of soil what is the effective saturation, that is our intention. So, before infiltration started, soil was having a moisture content of theta I that we are substituting and we are finding out the expression for effective saturation. So, it is SC is equal to theta I minus theta R divided by theta E. So, from this expression we can get theta I minus theta R is equal to SC theta E implies theta I is equal to theta R plus SC theta E. Because for a soil at a particular time theta R is known to us, effective saturation is a constant value and effective porosity that is eta minus theta R, that also will be known to us. From that we can calculate the initial moisture content. Otherwise, there are certain relationships between soil moisture content and the suction, soil suction, that is represented by soil hydraulic parameters. So, I am not going deep into that particular topic. You will be learning that in soil mechanics or unsaturated flow related topics coming under geotechnical engineering. So, then you will be able to correlate these things. So, here I am just explaining that theta I can be calculated as the sum of theta R plus SC theta E. Now, we were having a term delta theta, that is the soil moisture deficit in the Green-Ampt equation. So, that is nothing but eta minus theta I. This delta theta we have substituted for eta minus theta I when we were deriving the continuity equation. So, this expression we will modify a little bit by substituting for theta I from this equation eta minus theta R plus SC theta E. So, here we are having eta minus theta R plus SC theta E, but we know theta E, that is the effective porosity is eta minus theta R. So, eta is nothing but theta E plus theta R. So, porosity is written in terms of residual moisture content and effective porosity. That we will substitute in this equation. So, it will be taking the form theta R plus theta E minus theta R plus SC theta E. Even though we do not know the residual moisture content, we can go ahead for finding out delta theta. So, we want to discard this theta R from this expression. So, this theta R gets cancelled and it will be taking the form theta E minus SC theta E, that can be written as 1 minus SC into theta E. SC is the effective saturation and theta E is the effective porosity. So, if these values are known to us, we can calculate how much is the soil moisture deficit delta theta. So, here I am winding up this lecture. The reference related to this particular topic is Applied Hydrology by Venti Chow. Thank you very much.